Our next speaker is Eyal Kazin. He's a student at NYU, and he's going to talk to us about the Sloan Digital Sky Survey and some interesting results related to baryonic acoustic oscillations in large-scale structure in the universe.
Okay, thank you, Mike, for the introduction. So yeah, I'm here to talk about systems on slightly larger scales than before. I'm going to talk about large-scale measurements of the universe, which are very interesting because we can infer from them the evolution of the cosmos. One of the main goals of my talk is that you'll have better appreciation for this illustration over here, which kind of shows our current understanding of how the universe has been evolving. I'll do so by explaining how we use the distribution of galaxies to learn about the geometry and the expansion of the universe, and how we relate it to this picture over here, which is the cosmic microwave background that you all probably heard of, which gives us a picture of the universe as it was when it was 1,000 times smaller than the present. So when I was building this talk, I was trying to think what I have most in common with people in this room. And the first obvious thing that came to mind is that we all like to solve problems. And in order to solve a problem, we'd like to have as much information as possible to analyze. And at the end of the day, we want to compare our results to some fundamental concept. In the next slide, I'll show a movie, but it runs kind of fast, so I'll just give a brief introduction to what it is. We'll be focusing on an image of Whirlpool galaxy called M51, about 23 million light years away from us, and we'll be zooming out. And it's just to give you a broad idea of how much information is actually publicly available. And as we zoom out, we see a lot of little dots. Most of them are galaxies. And during this talk, I'll try to convince you we can use it to analyze the universe on very large scales. So this movie, this imaging is based on data obtained by the Sloan Digital Sky Survey. And this movie in particular was constructed here in New York University by my advisor, Michael Blackton. So this slide over here is similar to the first slide that I showed. Ongoing surveys like the Sloan Digital Sky Survey are measuring larger and larger chunks of the universe, transforming cosmology essentially into a precision science. And one of the most important measurements is the way that matter is distributed, and we can relate it to the cosmic microwave background, which I'll explain more in detail later, but for now I'll just give you a general idea of what you're looking at. These are when we look at the universe when it was 1,000 times smaller, we're looking at, we have this radiation that we're measuring all around us, and it's radiation we can translate, of course, to temperature. And we measure the universe to be about at 2.73 degrees Kelvin, but we're interested in where is it non-uniform, because it looks pretty much homogeneous and isotropic. But in order to understand structure, we need some breaking of the symmetry. And so these are cold and hot spots that we see only after we take off layers at the degree of 1,000%. So that shows how uniform the universe was back then, as opposed to the structure that we see today. So what you're looking, this movie over here, time is not evolving, but rather we're zooming in and now zooming out of a simulated light cone slice of the universe. This is a simulation of how we think dark matter is distributed. So you see at large look-back times, there's very little structure, and due to gravity, it builds up to the present day where the observer is. And so there's a lot of cosmological information within the distribution of matter. For example, we can learn about the constituents of the universe. Astronomers claim that atoms and radiation contain only 5% of the energy budget of the universe, and I'll show you why we think that. And we can use it to measure the cosmic expansion, and we can also test general relativity on very, very large scales. So this is the outline of my talk. I'll talk about using two-point statistics in measuring the correlations between the galaxies. And I'll talk about this very exciting feature here within the autocorrelation function. It's called the baryonic acoustic feature, which is a firm prediction of our standard Big Bang models, and it has recently been detected. This is my analysis. I'll also use similar statistics to explain why this plot over here is a way for us to test general relativity on very large scales. And I'll also say a few words about the Sloan Digital Sky Survey, which is a revolutionary survey that has industrialized in a very positive way the way we do analysis in astronomy today. So just a brief background, the relationship between physicists and astronomers. For the most part, physicists have been telling the astronomers what they should be looking up in the sky, for example, black holes and neutron stars, for the reason that the cosmos gives us extreme laboratories that we can't reproduce here on Earth. But here and there are examples where the astronomers are pointing up at the sky and telling the physicists about inconsistencies. A classical example is that, Mercury's evolution around the sun, Newton's theory of gravity was inconsistent with that. And Einstein, the first thing that he did actually with general relativity, he post-dicted the precession of Mercury to see that his theory actually makes sense with observation. And of course, later on, it was a big triumph due to predictions. So now we're in a similar situation in which astronomers firmly believe that of the existence of dark matter. We still don't know what it is, and that's why we're pointing to the physicists to give answers and to actually measure it directly. Dark matter does not interact with photons. That's why it's dark. We don't see it. But we can infer it through various gravitational effects. And another even more mysterious substance we dub dark energy, which we use it to explain why the universe is expanding the way it is. So why do we believe in dark matter? Again, here I just show a few of the many examples of how we infer it through gravity. For example, how the manner, rotation curves, the manner in which stars go around their black holes, within their galaxies, the way that matter bends light according to general relativity. We call it lensing, and so we use dark matter to solve these problems. And also motions within clusters. This is the poster child called the bullet cluster. I will focus on, in my talk on the way that galaxies are distributed, and that's another firm condition of dark matter because the way it's related to the temperature fluctuations in the cosmic microwave background. If you're not up to date, well, we've known for a while that the universe is expanding. This is a brief summary of the evolution of our understanding of this concept. So I'll just point out major milestones. 1929, Hubble found an interesting correlation between the distance to galaxies to the radial velocities, and from here he post-dicted that the universe might be expanding, but that's a post-diction. In order to convince the community, you need to confirm a prediction, and that's what happened in 1968 here in Homedale, New Jersey, in which it has been predicted that we should measure uniform radiation around us, and Penzias and Wilson measured just that. And then you can ask the question, okay, the universe is expanding, but at what rate? And what threw everybody off is the fact that in 1998, two independent research groups used relationships between distances and redshifts of exploding supernova and realized that the universe is accelerating. And so that really threw everybody off, and various other measurements have confirmed their conclusions. So how long has it been expanding? Well, for the better part of half of the age of the universe since the Big Bang. And there's also this, at the very early stages, this era of inflation, which is consistent with current observations. So just to give you a feeling for what I'm talking about, here I show the scale of the universe as a function of time. And so we see that there's this inflation era in which the universe is expanding really rapidly. And then we have this deceleration, which actually is the thing that makes most sense to us. Because if you have something that's massive and expanding, you expect it to pull on itself just through gravity. For example, take a grenade, let it blow up in space and without anything going around it. So you eventually expect it to pull on itself and decelerate in its expansion. So that's what happened when the universe was matter dominated. And what throws everybody off right now is that suddenly the universe just jump kicked around when it was about twice as small as it is today, and it started accelerating, and we're still in that phase of acceleration. And what one of the things we want to know is, will it continue to accelerate in the same rate, or does that rate change to a big rip, or maybe perhaps to a big crunch? And so those are things that we're interested in measuring. Why is the universe accelerating? Well, we don't know. Just mathematically, if we put in Einstein's original fudge factor, the cosmological constant, then everything works hunky-dory, but there's really no physical motivation behind that idea. Another thing that people are working on is modifying general relativity. Maybe it breaks down at large scales, and that's something that I'll try to convince you that we have a method of testing if general relativity is the real deal, not only on solar system scales, but also the universe at large. And I'll do so by measuring the geometry of the universe. And so this plot here explains one of the confirmations for why we believe in the existence of dark matter. Here I look at the recent universe, the way the galaxies are distributed. This is an angular map. Could we turn off the light? Maybe
at the back.
Thanks. And so here we look at overdensities, which I'll soon define, which is order between 1 to 10 to 100. And that's so you see a lot of structure over here, but the structure that you're looking at over here, these hot and cold spots, that's at the order of 1,000%. And so in order to go from here to here, just through the gravitational instability theory, we don't have enough atoms in the universe, but if you put into the equation dark matter, then we do get this. And yeah, so I mentioned that cosmology is in the age of being a precision science, and this is the leading theory, our Big Bang model, we call it the lambda CDM, based on dark energy and cold dark matter. And just to give you an idea of what kind of plots we're looking at, well, if we look at here, we're looking at matter density versus the density of dark energy, assuming it exists. Then if we look at results from the temperature fluctuations in the CMB, large-scale structure, this feature that I'm going to be talking about, the baryonic acoustic oscillations, well, they intersect. That's not too exciting. That's 2 lines. But if you add a third independent measurement, the supernova distance redshift measurements, then you see that they all agree pretty much. We're still investigating this, but it is very cool that we see that this model, based on very simplistic ideas, is consistent with many observations. So before I continue, I try to keep at a minimum my astronomy jargon, but there are just a few words that I'll be using time and time again, so I'll just briefly go over a few important concepts. In the expanded universe, how do you define distances, right? So we talk about co-moving distances, and a good 2-dimensional analogy in order to understand what that means, just to take a surface of a balloon, draw grid lines on it, and points in the middle. Let's say that this is your Milky Way, and you're looking at 2 other galaxies in this expanding balloon. Well, let the balloon expand. Well, now your grid lines are at larger distances, so instead of x, you're looking at a times x. And in order to make sense of everything, you can just neglect, when you do your calculations, you can drop the a and just talk in units of x. And so that's your co-moving distances, because that will be a constant in your expansion. So the units, I'll try my best to give everything in units of light years, because that makes a lot of sense, but astronomers are pretty much prone to using parsecs, and so this is the relationship, order of factor of 3. I'll be talking about very large scales, so that's why I'll be talking about megaparsecs. And this H inverse, if you see it, just neglect it, that's just the constant that we use. An important concept is redshifts. The universe is expanding, and so the radiation, so the wavelength in the universe is expanding with it. So that's our proxy for distances, and so that's also our proxy for time, because in relativity, time and distance are related. And also, I will do the common blasphemy, in which I will talk about baryons as a collective for electrons and protons as opposed to dark matter. So I hope that's all the jargon I'll be needing to use. So this is a nice poster which demonstrates on various scales how we think that dark matter is distributed. When you look at very large scales, you see that, it looks pretty much uniform, but as you go to smaller and smaller scales, right, I'm still talking about 23 million light years across, you see halos and you see filaments. And so it looks like this cosmic spider web, which we understand due to gravity. And so you want to quantify this in some manner. So you can think of every grid point, you define the overdensity, meaning in contrast to the mean density. And then if you want to analyze this in the same way, you want to use endpoint statistics. So I focus here on the two-point statistic, in particular autocorrelation function, defined right over here. And what this means is that if at a given point x you measure an overdensity, it's the joint probability that you measure an overdensity at a distance r from it. And so this is what most of the plots will look like. This is the scale distance r between 2 points, and this is the autocorrelation function. So it drops pretty much monotonically as one expected to gravity falling like r squared, inverse r squared. But most of this talk I'll focus on this very exciting feature over here called the baryonic acoustic feature, which contains a lot of early universe physics within it. If you're more familiar with the power spectrum, well, the Fourier transforms of each other, where this delta function over here becomes these ever slight wiggles. So in k-space, it becomes wiggles. And so technically, what do I mean by calculating the correlation function? I'm not looking at a smooth field, but rather I'm looking at point dots. So I do have Poisson shot noise to worry about. So what we do is, these are actually location of galaxies that I use, about 3 gigalight years from us. Here you have the scaling. And so what I do is I count galaxy pairs within a given radius. And so I count these data pairs, and I compare them to a random catalog. And the points of the random catalog is you have boundary conditions, and you have this weird mask, because, for example, you want to exclude bright stars and all kind of funky things that are going around there. And sort of understand your mask, you want to populate the areas that you know that you should have measured a galaxy with a random point. And so you want to use much more random points than your data points for obvious Poisson reasons. And so if I go back to my definition of the autocorrelation function, then our estimator in practice, I should have had a hat over here like physicists like to use, is comparing your data pairs to your random pairs. And it has been shown, if you want to minimize your variance, a better estimator is comparing also your data random pairs. And so unfortunately we can't see. Dark matter doesn't interact with radiation, so it's not luminous. And so we have to use luminous, what we call tracers, something that traces dark matter like a tip of an iceberg to everything under the water. And so what I focus here on galaxies, but there are other sorts of tracers that people are using to analyze. And we believe that we have good reason to believe that these luminous tracers aggregate at the deepest potential wells of dark matter, and so that's why they trace the same structure, and we expect similar correlation functions. So I mentioned a few times the baryonic acoustic feature, and so right now I'll rewind your brain to the early universe and explain to you the physics behind this feature, so I can explain why it's such an exciting thing to measure. So in the early universe, it was very much homogeneous and isotropic. It was very much uniform, but due to quantum fluctuations, you had these slight overdensities. And so here, I think a very ideal case in which the whole universe is uniform except for this one place at the origin. And so at the origin, just imagine that your universe consists of only dark matter, radiations, and baryons. Again, collectively, electrons and protons. And so what you have is, and here I show how they propagate outwards in a spherical motion. So as time evolves, you have the radiation propagating outwards. The dark matter stays in place, but the radiation does interact with electrons. So they're pressing on the electrons, which are dragging with them the protons. And so collectively, they're this plasma acoustic wave going by the speed of sound. They propagate for about 100,000 years from the origin. But remember that at the same time, the universe is expanding, and hence it's cooling down. And then the first atoms formulate. And so the importance of this is that suddenly the universe becomes from opaque for the radiation, where they always bombarded and hidden things, suddenly the universe is transparent. And so these photons that are propagating from here, we call this the surface of last scattering, actually are transparent and going up throughout the universe, and that's the cosmic microwave background that we actually see today. And so that was that firm prediction. That's why everybody was so excited when they measured the cosmic microwave background. And so what this means is that the photons, again, they propagate freely, but as for the atoms are concerned, they kind of come to a halt, and they leave this signature radius, we call this the sound horizon, in which now they're bound gravitationally to the dark matter, so the photons keep on going away, but the baryons kind of stay in place, and again, they cluster up with the dark matter, and so this is the profile that you expect from the matter in general, and then you'll have this ever slight peak over here, and the importance of the amplitude of the peak is that it gives you the ratio between how much matter there is, how much dark matter there is in the universe compared to the regular atoms. And so you have two scales. You have the amplitude and you have this radius scale. And so both of them are important for our understanding. So before I show you the correlation function of galaxies, I want to get back to the cosmic microwave background. Again, these are temperature fluctuations. So you have cold spots in blue, red spots, cold spots in blue, hot spots in red. And so in the blue spots, you expect to have more matter. And so this plot over here is one of the most, I think, amazing measurements in astronomy, perhaps I don't know if I can say in this audience in science in general, but it is very amazing that what you're looking at, these are the baryonic acoustic features within the temperature fluctuations. So this is a two-dimensional projected K-space measurement in which what you're looking at the correlation function of these hot and cold spots, and you see that the lambda CDM prediction, this is based on I think 6 parameters or something like that, shows a very nice fit to the data points. And so that's when I talk about precision science, this is exactly what I'm talking about. So this is the early universe. This is the age of the universe at 300,000 years, and we can relate that to the recent universe. And this is a very exciting measurement that came out in my first year in grad school. 3 people in NYU were co-authors in this paper, leading author Daniel Eisenstein, now in Harvard. And so these are the data points. This is the correlation function I talked about before, and this is the feature. This is what they got back then, and this is midway through the survey of the SDSS, and comparing it to lambda CDM models. Here, different models, he just changes his ratio between omega and between matter and atoms, and so it's a very exciting measurement, and a lot of it caused a lot of excitement within the community, and many surveys are underway to follow up on this measurement. So again, just to summarize what he's doing, he's looking at how galaxies are distributed, and going back to the early picture of the universe, the early universe physics, in which you have this overdensity. Just think of like dropping a pebble into a pond. You have this wave propagating outwards, and then kind of think, not a perfect analogy, but think that the pond suddenly freezes, and so you have this signature radius around this overdensity, and of course it doesn't happen in one place in the cosmos, it happens everywhere, and so by eye you won't see anything too interesting, you won't see these circles by eye, but statistically you expect to measure it, and that's exactly what they did, and so this is important for 2 reasons. First, it's a very firm confirmation of the lambda CDM model and our understanding of the gravitational instability. And second, it's practical because we can use it as a standard ruler. Why? Because it gives us a signature, a characteristic length in the cosmos, which we can use. And so this is a good cartoon to have in mind. If this is what I mentioned, the surface of last scattering, remember again, that's when the universe went from being opaque to radiation to transparent. So those wiggles that I showed in the temperature fluctuations, we can calibrate that as a standard ruler at a very high redshift. And then if we bring this ruler down to the recent universe, if we measure clustering perpendicular to the line of sight, then we can measure the distance to the mean of our galaxy. Why is that? Because this is simple geometry. If you know this distance, again, through the cosmic microwave background, you know your observer's angle, so then you can infer the distance to the galaxy. So that's one thing you can do. An even more exciting thing you can do is measuring clustering along the line of sight, and you can use that to measure the expansion rate of the universe, because measuring things along the line of sight is sensitive to the rate in which the universe is expanding. And so you want to measure clustering both transverse and in the line of sight. So, like I said, many surveys are underway to follow up on Daniel's measurement. And so Daniel's measurement, so here in this plot I show redshift. Again, that's the look back time, how far deep in the universe you're looking. And this is the first survey volume. Later I'll explain the importance why you want a large volume. I can mention right now, just you're looking at modes in a box, and so you need a large box to measure perturbation modes. So Eisenstein's measurement was basically on this sample over here, just a bit smaller in its value. There's an initiative in Australia called the Wiggles, and they recently reported measurement. And I'll show you my measurements just about up here, a slightly larger volume, and I'll show you predictions, what we should be expecting by 2014 by the next phase of the SDSS, a project called BOSS. So just to show you other independent measurements by the Wiggle Z group and another Australian initiative, the 6DF, in which they all show a similar signature exactly where we expect it to be. So we have measured it, and we just have to bash down the statistics by getting larger and larger volumes. So this is my playground. This is the galaxy sample I've been analyzing for the past few years. What you're looking at, this is the sky distribution. It's about 1/5 of the sky. This is an angular projection just to get a feeling for what's going on in the radial direction compared to the CFA, which in its day it was a revolutionary survey. So this is we're looking much further back into the universe, and I'll show results on that as well as predictions on the baryonic oscillation spectroscopic survey, or BOSS, which is going much further back into the universe. And it will cover up just more of the sky. And it's going to be 3 times as dense, and that's of course important due to Poisson statistics. And so this is my
Can you spec it to the website?
yes.
Can
You have a question?
you just explain that one more time? What BOSS is going to do?
So in BOSS we're gonna the bottom line is we're going to get a much larger volume of the universe. I'll later talk about cosmic variance and explain why we want larger volumes, but we're just going to get a bigger chunk.
But are you going to still contain the 2/5 of the, still going to keep the same numerical thing? You're just going to look at what data in that same slide, right?
So sky coverage, it's going to be similar sky coverage, just about 20% more, but yeah, but we're going deeper. Yeah. So this is my measurement using a larger volume than what Daniel got. So here you can see my data points, and you want to compare that to the lambda CDM model, the blue line. All these uncertainties are covariant, meaning if one point goes up, then all of them go up. And so what I did is I could pinpoint. I found I could measure the peak to an accuracy of about 3%, and I could infer the distance to about 3.5 million light years from here to an accuracy of about 3.5%. Yes?
Yeah, I don't mean to interrupt, but just as a quick clarification, the baryon acoustic feature was formed when inflation occurred, and then it's frozen in its current scale at the surface of last scattering.
Yes.
So this is measuring pre-inflationary cosmology to some extent. The distance, or the size scale that you're finding in this
Yes.
peak is helping to constrain inflation,
Yeah.
or pre-inflation cosmology.
Well, inflation predicts Gaussianity initial conditions, and that's something that people are still trying to measure.
Right. So that's what.
But yeah, I mean,
Thank
right
you.
now it is consistent with inflation, but there are ways of ruling out inflation. So we're still at the phase in which we're collecting more and more data to get better constraints. But yeah, but it shows that it is consistent with inflation.
Thank you.
Yeah, thank you for the question.
Sure.
So I mentioned a few times cosmic variance, and so those are these gray bands that you're looking at. They're 1 and 2 sigma uncertainties due to the fact that even though we have a really huge chunk of the universe, it's still not large enough to make precision measurements such as these. And the reason is we're looking at perturbation modes within a box, and like any other modes in a box, you want to have a larger box to get more modes and so to get better statistics. And so that's why surveys are getting larger and larger volumes. So a few words. How am I in time?
10 minutes.
Okay, good. Okay, so the Sloan Digital Sky Survey, like I said, one of the most important sky surveys is today. It's based on a 2.5 meter telescope in New Mexico. They currently released their final imaging, after over 10 years, the final imaging has been released, so that's publicly online, and this is what it looks like. So what they did, the first step was they imaged the sky, so that's kind of a blind process, they image it, and so that gives you, amongst many things, it gives you a two-dimensional mapping of the sky. And the next phase is you want to identify objects, and then objects of interest that you want to get spectra from. You follow up by measuring the spectroscopy, and so there, of course, there's many things you can do with spectroscopy, like identifying elements, etc. But from my analysis, the most important thing that comes out is you get a 3D mapping of the universe, which is important because through redshift you get a proxy of distance. And what I mean by redshift is that many galaxies have similar fingerprints. Like this is the spectrum of actually galaxies that I use, the luminous red galaxies. And it just, if you the further away they are, the more they're shifted, Doppler shifted towards the red, and that's why redshift is a proxy for distance, and that's how we get our three-dimensional maps. And so just a few, SDSS in numbers, all this is available currently. So like I said, all the imaging is available. So that's summed up by about 60 terabytes in data. And spectra-wise, everything's in like 5.5 terabytes. And this is just the number of objects, which is an amazing amount of galaxies, quasars, stars. So back to science. So I mentioned before the importance of measuring the baryonic acoustic feature in the line of sight in perpendicular, meaning as a function of angle, but yet I regarded angle so far. I averaged that out. And so now I'll talk about the importance of the angle and how we can actually use that in order to test gravity on large scales. And so what you're looking at over here is a very boring plot of what one would measure clustering. This is a contour plot. Taking the angle into account, so the y-axis is the separation, the x-axis is the deviation from the line of sight. Meaning, and so here you have strong clustering going down logarithmically, and so the line of sight is at theta equals to 0. The baryonic acoustic feature in this plot, if you were trying to look for it, then it would appear as this stripe over here, because you're going down, you have a bump. I should change my color code because it's hard to see from where you're sitting. And so the baryonic acoustic feature perpendicular to the line of sight, which you can infer distances, is over here, and the feature along the line of sight, which you can infer the expansion rate of the universe, and hence analyze dark energy, is right over here. And so we will never get a measurement like this in the universe. Reason being is that I mentioned we use redshifts as proxies as distance. But we're doing one thing wrong in these calculations, is that we're assuming that galaxies follow the Hubble flow. But that's incorrect because they're also affected by local dynamics. And so, an important effect is that imagine that you have a supercluster over here and you have field galaxies, let's say 60 million light years away, and they're all being pulled inwards by its gravitational pull. And so this is in real space, what's actually happening in the universe. What we will see in what we call redshift space is that the ones on the line of sight from the observer will appear to be more clustered in. So that means that we see things closer than what they actually are, and that of course affects your correlation measurements. And so this, according to linear theory, what we will actually see in redshift space. So you see a lot of much more interesting features. For example, this negative C, here it goes negative at very large scales. Here at much smaller scales it goes negative. The baryonic acoustic feature, which is a strip over here, is these funky looking ridges. And so looking at n-body simulations, now you see a lot of linearities coming into play. Like these ridges become much more wide in the baryonic acoustic feature. You have non-linearities down here. You have a very similar trend over here. And this is actual observation. This is the largest measurement that we currently have of clustering of galaxies. And so you see we have this negative C. We have these non-linearities on small scales. We have these influx that we see off the line of sight. So you see that we're in the correct direction, that we understand, at least in linear theory, what's going on. And so on the one hand, these redshift distortions, as we call them, they complicate relating between the underlying theory to observations. But fortunately, as we do a lot of time in physics, if we understand what's causing it, we can learn about the progenitor. So for example, the reason for these distortions, again, are the influx of these galaxies, and that's due both to the matter abundance that's causing these velocities and to the other underlying gravitational theory. So that means that if we parameterize how much redshift distortions there are by this squashing parameter, we call it the squashing effect, then we can use it, and then it has been shown that it goes by the abundance of matter and by the underlying gravitational theory. So general relativity, for example, will give you some value. And so that's this is a parameter, this beta parameter is something that we're very interested in testing. And so that's what I'm working on these days. One test is using these observables where before, if I focused on the angle average, meaning the monopole, I can compare that to the quadrupole, which is just, again, counting pairs. Now you're using a weighting of the second Legendre polynomial to take into account angular dependence. And notice that if these each independently depends on scale, according to linear theory, this combination gives you a right-hand side that does not depend on scale. It depends only on beta quadratically. Again, beta is a proxy of general relativity.
What's the DGP model?
The DGP model is a modified gravity for testing general relativity. It was formulated actually in NYU by three professors, Dvali, Zabe, and Parati. And they're actually extending general relativity into 6 dimensions. And it's a way to explain the expansion of the universe, the accelerating nature of the universe without dark energy, but rather that energy is going into higher dimensions. So these are results from n-body simulations. And so this is the statistic Q, meaning the quadrupole over the monopole. And as you see, according to n-body simulations at very large scales, it becomes flat. This sharp signature is due to nonlinearities, which aren't taken into account in this theory. And so this is what we get according to simulations. And this variance is again due to the limited size of the volume, meaning this is cosmic variance. And this is what I get currently with observations. And I'm still analyzing this, but you do see there's no fitting over here. This is just the Mach mean. I didn't do any fitting, but just to give you a perspective of what this means by flat. And so it's pretty, you see it's pretty much jumbling up over here, but it's on the correct scale. But you do expect it again due to this cosmic variance. Okay, so I'll just summarize with these last few slides in which I showed you measurements of clustering of galaxies using the autocorrelation function and using it to test out geometry of the universe through this very exciting baryonic acoustic feature, which has been detected in various surveys. SDSS were the first ones. And these gray bands is our current cosmic variance. So this is so it's not a significant measurement yet, but it's definitely we're seeing exactly what we expect to see. And we can use this to test geometry. For example, we can measure distances and the expansion rate. So this is current kind of constraints that I get from simulations. I get to do it on the real data. And I talked about the fact that you can use these two-point statistics also to test general relativity on very large scales through this beta measurement. And so now I'll fast forward to 2014, what we expect to get from the next phase of SDSS from the BOSS project. And this is from simulations. This is the cleanup that we expect to see. So I'll just toggle between them, and you can see how much, again, this is due to the fact that we're reducing cosmic variance. Plus also Poisson statistics, because we'll use a sample 3 times as dense.
You expect it to be like 600 terabytes, but it's supposed to 60.
Oh, I never looked into those. I don't know. Well, actually, I
You said
can't.
it was 60 now.
Well, I can't offhand say because they finished already all the imaging, so there won't be any more imaging. In most of what comes to terabytes, most of it goes into the imaging, so that they already finished. The next phase is only spectroscopy. The SDSS has 4 projects. The BOSS that I talked about, and also measuring planets and analyzing also the Milky Way. So those two projects that do that. So, but imaging-wise, they finished.
How long does it take them to take individual spectrum?
What?
How long does it take them to take an individual spectrum?
So that's a good question. So the minimal, I think, is they look at each object 15 minutes times 3. But then it has to go. It goes by signal to noise. They have a certain threshold in which they want to measure And so then they decide on the spot if they're going to take more time at a given point or they want to move on to the next region in the sky.
It's gonna take a while.
It's highly multiplexed.
Yes.
Okay.
Okay.
Yeah. Okay.
Yes?
Depending on
I'd like to follow up on just the physics of the acoustic peak itself. And forgive me because my understanding is so shallow. If you go back to the previous plots where you showed your peak at about 110 megaparsecs or thereabouts, what is the original peak way at zero? In other words, you're going all the way up. That's the original. Is that the Big Bang?
Well, so imagine that the universe is
Right.
It's
If you go
uniform,
back
but you
to
have
the-
quantum fluctuations. So it's a quantum fluctuation.
Could you just go back one or two slides real quick so we can see, or is that too late?
I'll do it just after I just
Yes,
finish,
please do.
my
Yeah.
presentation.
Oh, okay, you're not done yet. I'm sorry.
Yeah.
I apologize. I thought when you put that up, you were already finished. So.
No, I have just two more slides.
Sure.
Sorry.
Sorry.
So yeah, so as I promised, my goal was to have a better appreciation from what's going on here, and this is our current understanding of the evolution of the universe from the surface of last scattering. I did talk about what happens before, what generated these hot and cold spots, and basically this is the structure that we see today in the form of dark matter. We don't see dark matter directly, but we use tracers. For example, I use luminous galaxies and use that to infer the geometry of the universe through the expansion. The universe is accelerating, and so we can use this to measure, is this modified gravity or is this dark energy? And for those of you who are interested in the SDSS, and this is the site, sdss3.org, so feel free to go around. If somebody wants to be active in some way, then a cool project is called Galaxy Zoo, a side project of the SDSS, in which it's one of these trends that they're using the public to analyze data, because the human mind today is still better than computers at identifying objects. So they have, you don't need any background in astronomy. They train you for whatever they need. For example, they show you a spiral galaxy. Is it going this way or is it going this way? So they use all kinds of cool statistics like that to learn about. And they have just about over 300,000 users already worldwide. So yeah, so that's my talk, and I think we'll talk offline about your question. That's how much time do we have?
I think like 2 minutes or something. Maybe we could have another. We could have one more question, maybe. But Charles, you've already asked a
Yes,
tough question.
Yes, I let other people. Yeah, that's
If
fine.
nobody else has any questions, we can ask.
There's one right behind you.
Okay.
Quick question. So we're using the 2-point correlation function.
Yes.
Is there been any advances with using more points or
Yes.
pattern matching circles or
Yes.
anything like that?
Yeah, so people have been publishing the 3-point correlation function, for example, and it's important because, for example, if you want to measure the filaments in the universe, you can't do that with the 2-point correlation function because it totally disregards that. But if you have 3 points, then you can see, are they aligned in a filament or are they distributed in a more random fashion? So yeah, that's a good question, and there's actually more things that one can do with higher order statistics, of course, but also it's much more complicated.
Yeah,
We have
peculiar
complicated
motions.
masks.
You get peculiar motions.